Hello everyone. In the previous classes, we have finished how to learn about the wave-particle duality. We have learned different factors on wave-particle duality. Today, we have to solve the numericals. So today, our focus lies on the numericals of wave-particle duality, that is chapter 24. Clear? So let's see, the set of formulas we will use is not much different from the photoelectric effect, except the new introductions by the de Broglie hypothesis. The formulas we will use are very known to us, that energy, please note down these formulas because they will be very helpful while solving numericals, equals to h nu, also energy equals to hc by lambda. These two formulas are very much important for the energy, and along with that, in this chapter we will also use the Einstein's equation between mass and energy, that is E equals to mc square. So these three formulas are very much important for energy. Clear? In any case, if you are asked in terms of frequency, yes, this gives you the frequency. If you are told in terms of wavelength, there is a formula for lambda. And in terms of mass, if you are calculating, these are the values. Next comes to the formulas for momentum. In case of momentum, what we will find? We will find out that momentum is always mass into velocity, and hence we got c equals to h nu by c. Also we have got in terms of wavelength that p equals to h by lambda. I'm sorry for the writing. And also have found out the formulas of calculating the wavelength from here, that we can also find out the wavelength if we know the momentum. These two are basically same formulas, just inverted to each other, written it twice because they are very much important. And lambda equals to h by p, that means lambda equals to h by mv, that is mass times velocity. Clear? So these are the formulas corresponding to the energies and momentum. Now let's come back to the next topic, that how to solve the Broglie wavelength of electron. Now when we are working the numericals on electrons, we must need to use the following formulas for them. Just like, because if an electron with mass m and moving with velocity v, what to find in their formula? Let's see. Say here that the kinetic energy of the electron is normal equation. Kinetic energy is half mv square. And from here we get the formula for velocity, that is v equals to root 2k by m. Next, we can also find the de Broglie wavelength, lambda was h by p, that was h by mv. So if I put the value of v here, we are left with h by root 2 m k, where k stands for the kinetic energy portion. K stands for the kinetic energy part, and that's the equation for wavelength of electron. And if we express the kinetic of the energy of the electron in terms of electron volt, that is charge time potential difference, then k equals to ev for an electron of charge small e, and hence the formula will become very important one. We must need to remember, in place of k we will write ev, it becomes 2m ev. It's a very important formula for calculation of the wavelength of an electron. A potential difference is given, we all know the rest of the things, because the mass of the electrons and each and everything are known to us. Clear? And if we put the values if we put the values of other things, just like what we know, that lambda equals to h by root 2m ev. So we all know all the values, that h equals to 6.63 into 10 to the power minus 34 is in the units of joule second, and the mass of the electron is 9.11 into 10 to the power minus 31 kg, and the put E electronic charge is 1.6 into 10 to the power minus 19 coulomb. We all know these values of the equations we use. So if I put all these values in the equation, I will find out that only the changing factor remains is phi. So except phi, we all know the values, and roughly the value comes out for lambda is 12.27 by square root of phi in the units of angstrom. In the units of angstrom, or in together we can also write root 150 by phi, just squaring it inside angstrom. So this is also an important formula for us while solving the numericals on the wavelength of electrons. So only these formulas are required, nothing else. Using these formulas we can solve a lot of numericals, so please note them down in your copies. So I hope there are only 10 numericals in the chapter. It will not take more than one classes to solve them. So I'm giving a couple of examples, like the question number 3. We can solve. A moving particle has a de Broglie wavelength of 1 angstrom. It is said the moving particle has a wavelength of 1.0, that is 1 angstrom. What is the momentum of the particle? Very easy. 1 angstrom means 10 to the power minus 10 meter. So that is the value of our wavelength now. Now the momentum's formula P equals to h by lambda. What is the value of h? The value of h is 6.6 into 10 to the power minus 34, and value of lambda is, we got just now, 10 to the power minus 10. So what if we solve it out? 6.6 to 10 to the power minus 34 by 10 to the power minus 10. Question number 3 continues. So we got 6.6 into 10 to the power minus 34, and the 10 to the power minus 10 in the denominator, when it goes to numerator, becomes 10 to the power plus 10. So the answer is 6.6. Oh, sorry, I have made a mistake. These are not lambdas, these are all p's, because p equals to h by lambda. So I put the values of lambda, so I'm calculating p. So 6.6 into 10 to the power minus 24 kilograms. I hope this is clear. So this is how we solve out the numericals in the chapter for calculation of wavelengths if the momentum is given, or the vice versa. Let's solve one more numericals from here. Let's solve one more numericals from here. That the question number 6. Question number 6 is quite easy. It's asked to calculate the de Broglie wavelength of an electron whose speed is 0.5 km per second. So the velocity of the electron is 0.5 km per second. We have to calculate the de Broglie wavelength. We all know that lambda equals to h by p. If mass is same and velocity is v, then momentum is mv. So I will just write it. Now I all know the values of h and m, just written in previously 5 minutes before in the lecture. H is 6.6 into 10 to the power minus 34, and mass is 9.11 into 10 to the power minus 31 kg. But one thing you have to be sure, that while writing the units, the SI unit is not kilometer, so we have to convert it into 0.5 kilometer to 500 meter per second. 500 meter per second, and if you have to write 500 here, not 0.5, because we are working with SI units. Now just a calculator problem left. The answer we will get, just nullify. This is not 34, this is 10 to the minus 31 my mistake. So the answer will come out to be roughly we get 1.45 into 10 to the power minus 6 meter, and that's the value of wavelength. Clear? So it's a basic problem. Next comes the question number 8. It is said in a diode valve the anode has a potential of 100 volt. The potential difference is V, and that value is 100 volt. So V equals to 100. Here asked to find the de Broglie wavelength. Formula for de Broglie wavelength is what? What is the formula for de Broglie wavelength? Is 12.27 by root V in the units of Armstrong. So I got 12.27 by root over of 100. What is root over of 100? It's 10 basically. So 12.27 by 10. So the answer is 1.227 Armstrong. Clear? 1.227 Armstrong. I hope the answers are clear to you now. So just using this formula, the one we derived little bit before, using the mass as you can see previously, if you want to forgotten by somehow. So that's how we solve the numericals. So I will ask all of you to please solve the numericals as soon as possible. Very less number of numericals. So your homework is all numericals. That is only question number 1 to 10. Please solve it by the next class. Thank you everyone. If there are any doubts, please inbox me.